Right, thank you for the introduction. Yeah, today I will be talking about my joint work with my advisor, Piotr Polesiuk, who is here today, on relational models for a particular variant of algebraic effects and handlers called effect capabilities. So I'll start by introducing a bit of our motivation here. So the way it usually goes in our field is that we think up some cool new programming language with some neat features, and then we take that language and put it into this big pile of mathematics. And a key thing that happened in this project is that we started the process of developing this theory early enough that it influenced the language design itself. So what people normally do with the math is they show some properties like termination or type safety, but we found that logical relations just in the process of defining the model really force you to think about the language semantics and how things actually interact, how they work, and not just how they look syntactically. And the language that we designed is called FRAM. The initial design goal was to improve the ergonomics of lexical effect handlers. We started with the theory pretty much straight away, and each influenced the other here. And a lot of other cool stuff happened in FRAM as well, but today I'll just talk about effects. So if you want to learn about FRAM, I invite you to Piotr's talk on Friday at the ML family workshop. So let's talk about this simple example of the reader effect. Unlike in the previous presentation, here the definition of the operation comes first, and then there's the handled code. Reader has a single operation ask. It is defined using a special kind of lambda abstraction. Here we take a unit argument, and we also explicitly name the resumption here. And then we can resume the calling code by giving back the value 21. But we don't need to immediately use effect to define the operation, or to use it like that. Since ask is just a regular first-class variable, we can pass it to functions, or we can have multiple instances pretty much for free. These are just normal variables. And we can do other things. Instead of using effect directly here, we can first do a type abstraction for the polymorphic raise operation for exceptions, and then return and then abort the computation and exit the entire program at this polymorphic type. Or perhaps you want effects with multiple operations like state. In this case, we can use records or pairs to accomplish that, and then put the effect abstractions into the fields. And one way to do that is do the usual trick of representing a stateful computation as a function from the value of state. And finally, once the handler, the expression under the handler evaluates to a value, it needs to agree with the type here. So once again, we have the return clause, which we can use to wrap it in a constant function. And then, once the big handle expression evaluates to such a function at last, we need to apply it to the initial value, for which we have an additional clause for handlers called finally. And here the initial value is 0. So let's get back to reader. What's the type of ask this capability here accessible for the handled code? Well, it's a function from unit to integer, but something we want the type system to provide us with as well is to ensure that we can never use the effectful operation outside of its handler scope. For this, we have the handle construct, normally implicitly, introduce an abstract effect variable, which is then attached to the arrows type here. in a way somewhat reminiscent of the ST monad, if you've seen that. And another feature we wanted in FRAM is first-class handlers. So we introduced them using the handler constructor like this. They can have the additional clauses and the handler's definition. And then we use the first-class handlers by writing handle with and the first-class handler. And actually, the syntax we used earlier is just syntactic sugar for immediately installing a handler defined here. So for the semantics, the first thing we do when we are trying to evaluate a handle expression is we generate a fresh runtime label for this specific handler, and we transform the handle into a runtime labeled version of it. It keeps the return clause unchanged. We transform the finally into a let for this runtime handle and the body after in. And as for the definition of the capability, it disappears from handle because it's substituted into the handled expression body and also associated with this specific label by this special translation here, which in this case looks something like this. We take the unit argument, and then we have a runtime version of effect with the label, which otherwise maintains the body. This is the resumption here. And some of you may already see that this is similar to the shift 0 and reset 0 limited control operators, and that's because this is exactly what they are. So what comes next? Reducing, we get a boring regex, let's reduce it. And then we have to evaluate the runtime labeled effect expression. So we have to capture the context up to the nearest handle with the correct label, and then evaluate the effectful function's body with substituting for R this captured continuation like this. So before we really get onto the logical relations, we still need to discuss the types a little bit more. Let's take this already partially evaluated handle with the runtime labels. Let's start with the smallest part. Here is the handled code in which we already substituted uses of this effect L expression somewhere. So this has some sort of a type and an effect, an input type and an input effect tau I, epsilon I. And that is also the type of the argument to return, which in turn, we have the entire handle, the labeled handle, the delimiter for this effect, which has the delimiter type tau D and effect epsilon D. And this is also the type used for the body of the return, for the body of the effect construct, and also in the resumption bound by effect. And finally, we have the finally, which turned into let here. So that accepts the delimited type and has some other potentially output type tau O and epsilon O. And this is an important picture because we'll keep coming back to these various types and how they interact. So we are now ready to think about what is the type of a first-class handler, as we've seen before. And that looks something like this. We have the distinguished effect variable, which is given by handle when typing in the language. We have the type of the capability, which doesn't appear here because we already translated it and substituted it into this, but it's stuff like that from unit to integer type for ask we've seen before. Then we have the input type and input effect before the arrow. And at last, we have the output type and output effect. And you may have noticed that this in-between type and effect of the delimiter do not need to appear in the handler type, because the programmer using a first-class handler can't really make use of this information in any way, can't interact with it, and it gives us a nice form of abstraction. Okay, with the types out of the way, we are ready to start interpreting them in the logical relation. We'll start with the notation for closed terms. And the way it usually goes, we have to interpret types as semantic types, here with some type variable environment, because we have type variables. And an interpretation of type is a relation on values which, in some sense, behave in a similar way. Then we have to extend that thing to expressions. Expressions also have an effect, so we have to include that. All pretty standard stuff so far. And the other thing that's already known in literature is we have to interpret effects somehow, and the approach we take is based on the paper Handle with Care. And here the relation is a little bit complex, so let's go over the little pieces. First, we have two expressions which directly raise the effect. They often look like this labeled effect construct. This is the thing that causes control flow to jump around pair-ups and stuff like that. Then we have two sets of labels, which are the labels on which the effect is raised and on which it needs to be handled, potentially. And then, at last, we have R, which is simply the type that's expected by the context once we return from the operation, if we do. And you also need an open variant. And once again, we do the usual thing of giving a semantic counterpart to the typing judgments. So we have the type variable naming technology. We have the type variable environment delta and the regular variable environment gamma. And we relate two expressions with an approximation relation, because that tends to be easier to work with, and there is a type and an effect. And it's done in the standard way by quantifying over all well-typed substitutions for the environments. The more complex part here is the semantic judgment for handlers. This syntactic category is the handlers that we construct using effect and pairs and so on, but without the return or finally clause yet. They can still be composed together, still using pairs and like that. They're not yet handler values. They're just something that's not yet frozen completely with turning into a first-class handler. And let's start on this side first. There's the capability type, as before. And this time, because we don't have return or finally, we have the delimiter type and the delimiter effect only. And then something complicated happened in the environments here. We have, once more, the normal type variable environment. Then there's the distinguished effect variable, which can appear perhaps in this environment, perhaps in this type. It could appear somewhere here. And then there's a second type variable environment of the type and effect variables bound after alpha. We realized its importance while defining the model, but the simple intuition here is that when we defined a polymorphic operation, like raised for exceptions, first we need to know what this specific effect is like as we define it, but we will only know its type arguments once we use it somewhere. So it all needs to happen in order. It's just much cleaner this way. So I will skip over most of the interpretations because they're standard, but let's focus on the handler type for now, type of first-class handlers. Obviously, handlers are in this relation, and we will work with them pointwise. First, we need to do something about these handlers here, these row handlers, and we'll do it not by looking at their syntax or anything like that, but we want to actually relate the capabilities produced from these handlers for specific labels. So we take any pair of labels, we produce the capabilities, and we want to make sure they are of the correct capability type. The little problem here is that in tau h, the type of the capability, obviously we want the special effect variable to appear. That was the whole point. So we need to somehow interpret it in the environment. And at first it was really non-obvious how to do that, but it turns out one reasonable approach is to just say there exists some effect. It fulfills some basic properties. Here, this property f says, in a very complicated way, that the stack expressions, the expressions raising an effect from f, can be handled by handlers labeled with these labels on either side. And the next thing are the return clauses. Something is missing here. We still don't have the delimiter type and effect because it doesn't appear in the handler type. So what we can do instead is once more existentially quantify over the stuff we expect for return, but it turns out that instead of separately quantifying over the delimiter type and effect, it's much more convenient to quantify over relations on expressions here, because certain equivalences become much easier, or perhaps possible in the first place, to prove. But we'll get back to that later. So here we use another helper relation R, which says that for any expressions of the input type, which uses this effect potentially, and the input effect, and additionally this special effect linked to this particular handler, if we put them into labeled handles at these labels, then with these return clauses, then the entire thing should appear in C. The entire thing should be related by C. And the last thing to do are the finally clauses. So this time we go over all expressions in C, and we put them into the finally clauses body. Since they're expressions, we bind them with let to sequence the computation. And then those entire complete things we have here should be of the output type and output effect. And the other part is that we still need the open judgment, which is a little bit different. No more return clauses, no more finally clauses, just the handlers, just the delimiter type and effect. And we have this environment here. So first we do the standard thing. We go over all substitutions, all type environments, semantic type environments here for delta 1. Then we consider every pair of labels as in the closed case, and the existentially quantify the semantic effect for this handler as before. And only then we can quantify universally again over the rest of the type variable environment. And it's pretty interesting that we have this quantifier alternation here. And it turned out really important for showing that the model actually scales for all the features we wanted, and in particular, polymorphic operations were something that pushed us to define it in this manner. Then the rest of it is mostly standard. We need any value substitutions that are related for gamma, and then the capabilities, this time closed with the substitutions, are related. Well, almost. Another small thing is, I hinted before that these handlers can be composed still. You can still build pairs of these things, But if we just use this particular effect here, it won't work because we may end up with two different semantic effects, and this requirement here is too weak. So we have to quantify overall super effects to get nice stuff like percent records. And another thing we ask ourselves is we can find a specific effect and replace the existential quantification. And it turned out we could by taking the largest effect we could think reasonable, which includes all expressions that are of this shape and fulfill some well-typedness requirements. But that was more, this model is still not perfect because we haven't been able to show some of the interesting equivalences by using it. So let's move on to actually seeing if the logical relations work. We'll prove some equivalences of handlers. We'll start with an example that uses the kind of reader implementation we've seen before, which uses effect. And then we use a different reader implementation, which introduces a new kind of handler that just creates a capability that's specified here directly. And this way, we can have pure handlers. And they have to be at the appropriate type and for any output types, any delimiter types, and any environments. So the key here for getting this kind of proof is choosing the correct semantic effect. And in this case, it turns out it's enough to produce a single tuple that contains the capabilities. Here's the pure constant function applied to unit, and here's the effect construct, which just turns back 42. And then the return type that we put back into the resumption contains just the pair of 42 and 42. And the even more interesting example is that we can show that the same pure reader again, now as a handler value, and a kind of weird state handler that still has the get operation, but has no put operation, and it has the return clause as before and the finally clause as before, that this reader is actually equivalent because we can never change the state. We can't produce its put operation from anywhere else. This is why it's important that we already added the return and finally clauses. And here we have to instantiate not one, but two existential variables. And the first is the semantic effect again. It turns out it's similar. You just produce the capabilities for these two things, and it works out. But the more interesting part is encoding the kind of computations that still haven't been processed by finally, but are already delimited, in which way you kind of encode the protocol enforced by finally. So here, we consider such pairs of expressions that are related at the output type and the output effect if we leave the first one for the pure handler alone and apply the second one to 42, just like in the finally body. And it turns out for this choice of computations, we can actually prove this equivalence. And this is the one that motivated defining the relation like this in the first place, because if we separated the delimited type and effect, we couldn't make it go through. So here are the things I hope perhaps have as the takeaways. One thing I learned in this is that development theory early is a great tool for language design, and that logical relations are an excellent tool for language design, not just the usual things they tell you about with proving things about the language. The other cool thing is that we have a fairly small and maybe not simple if you're just looking at the slides here, but comparatively simple and small model that can support all kinds of handlers that we haven't even seen. There's polymorphism, there's pairs, but there's also existential types and so many more things. There's recursion. And the thing that I didn't talk about at all is that maximal effect, which we talked about briefly, is actually a good model for the delimited shift 0 and control 0 multi-prompted operators with first-class labels. And another thing that was really helpful in this project is that we pretty much started formalizing the theory straight away, and it evolved along the way. We kept having to modify it, and something I have to say is that the upfront cost of that is really high, but being able to incrementally change the proofs was incredibly helpful. So that's what I wanted to talk about today, and now I'm looking forward to your questions.
Thank you. Do you have questions? Yeah.
Hey, thank you for your talk. I've been interested in this for many years, and I'm very happy to see your work here. That's really great. You have shown how to relate to different handler implementations, right? The reader, versions of reader. Do you have any insights or any experience reasoning about effectful programs, especially higher order functions, like say you have a program that uses effects or a program that is parameterized over a function that might use effects? How can you use this existential capability reasoning here?
Okay, so the background here is that initially we sort of neglected equivalences at all. We thought that just designing the model gives us the insight we need, and for a long time, we didn't really find the time to prove interesting equivalences. And this is all still a work in progress. And actually, these two equivalences are all really fresh stuff from the last few days, but formalized in Coq mostly. So we haven't really tried applying this technique to any larger programs.
Because in general, it looks like you have something like parametricity for existentials, and capabilities are very related to existentials, right? Because you pass things to a program that closes over things, but you don't know what.
Yeah.
So I'm very curious to see what you find out about users of handlers and reasoning about those. Because as a programmer, I want to reason about my programs that I write that use effects, but I don't know how they're handled yet. Thank you.
Thank you.
Do you have other questions? Maybe I've got one. So when we consider a language with mutable stores, there's all this work about Kripke logical relations, and often they are defined in, using a bi-orthogonal definition. And when you unwind the bi-orthogonality, you see this kind of existential appearing, like there exists a future world, kind of things. And I was wondering if it's related to the kind of existential we've got here. Like, would it be possible to use some kind of bi-orthogonal logical relations to hide this existential, or do you think it's not related?
So this is using bi-orthogonality in the usual way for dealing with algebraic effects, actually.
Mm-hmm.
I'm not really sure how to interpret your question. I don't really... I'd like to know more, but I don't really know what you mean by hiding the existential with bi-orthogonality here. Sorry.
Maybe you can talk about that offline. Thank you. We can thanks again the speaker.